If you're having trouble setting up triple integrals in spherical coordinates, this video is intended to help you visualize what those three spherical coordinates, rho, theta, and phi, look like in 3D space. We're going to start by looking at this point in 3D space, and the first coordinate we're going to look at is rho. Rho is defined as the distance from the origin, and you can think of it like a 3D radius, or later when we start making solids, this is going to be the radius of our sphere. Theta is measured the same way that it is in polar or cylindrical coordinates, where we start from the positive x-axis and we rotate towards the positive y-axis. You're probably more used to seeing this in 2D space, so make sure that you're starting it at the right position with the positive x-axis and sweeping towards the y-axis. The last coordinate, phi, is the angle measured starting from the positive z-axis. Notice that this description doesn't give us any direction for phi to travel like theta does. What this means is that the same phi can be measured at many different spots around the z-axis. In our example, phi is 30 degrees, but over on this side, phi is also 30 degrees. In fact, all of the points on this cone have the same phi value, 30 degrees, since the angle they form with the positive z-axis is always 30 degrees. Next, let's think about the possible values for our three coordinates. Starting with rho, we only want to consider positive values for our distance, so we're going to say that rho has to be greater than or equal to 0. In the diagram, you can see what happens when we let rho fluctuate between 0 and 1. Next is theta, and if we start at theta equals 0 and go up to theta equals 2 pi, then what we've done is swept in a complete circle, and that circle is going to encompass all of 3D space. So theta is in between 0 and 2 pi. The last one is phi, and this one might be a little bit counterintuitive the first time you see it, but it makes sense if you think about the values of phi needing to sweep all of 3D space. So if we start at phi equals 0 and slowly increase it, we can see this cone almost blooming out of the z-axis until eventually it reaches pi over 2. And when phi is pi over 2, then we've swept all the way down to the xy plane. And so if we then continue to increase phi, then we start to get this cone in the negative z. And at the bottom here, we've swept all of 3D space, but note that phi hasn't gone around in a complete circle. Phi has started at 0, but the angle of phi down at the negative z-axis here at the bottom is equal to pi. So we say that phi is going to be in between 0 and pi. If we put all these together to try and define a solid sphere of radius 1, then we can say that rho is in between 0 and 1. Theta is in between 0 and 2 pi, and phi is in between 0 and pi. Let's look at a few more solids where spherical coordinates would be a good system to use. This next one is the portion of a sphere that looks a little bit like an ice cream cone. The sphere reaches out to a radius of 1 at the edge, so we say that rho is in between 0 and 1. For theta, as we sweep around the z-axis, we see that the entire circle is present in the solid. So we say that theta is in between 0 and 2 pi. And lastly, for phi, since this cone forms a 45-degree angle, or a pi over 4 radians angle with the xy plane, we're going to say that phi, starting at the positive z-axis, is between 0 and pi over 4. These three ranges for rho, theta, and phi form the bounds for our triple integral. So we can find the volume of this solid by looking at a triple integral that is integrating 1. The last solid I want to look at is a quarter of a sphere. Again, rho is going to be between 0 and 1, but I want you to think and see if you can figure out what theta and phi are for this solid. If we let theta sweep around the z-axis, we can see that it starts at pi and then finishes at 2 pi. Phi starts below the xy plane, so our starting point or lower bound for phi is going to be pi over 2 at the flat xy plane, and then it's going to extend all the way down to phi equals pi. While I have this example up, I thought I would show you something interesting that can happen with rho. Let's say that rho in this case is between 1/2 and 1. Then we wouldn't start at the origin, we would start with rho equals 1/2. So we get this hollow sphere effect. Looking back at our quarter sphere, you may have noticed that this isn't the easiest way to find the volume of this solid. In fact, we know that the volume of a full sphere is 4/3 pi r cubed, and a quarter of that would end up being the volume of our solid. The major benefit of spherical coordinates is that we can introduce a fourth variable, our density, and we can talk about the mass of a solid. For example, if I let the density be proportional to 1 over rho squared, then there's no way that I'd be able to find the mass of this object. But spherical coordinates says all we need to do is change our density formula to be k over rho squared. One more thing to consider before you start trying to tackle these spherical coordinate problems is that when you're converting from Cartesian coordinates, x, y, and z, into spherical coordinates, you're going to need quite a few formulas. But a lot of these formulas are things you've already seen, or they're based on this following right triangle. So I'll lead you to the book or the online resources that I'm going to link below in order to see more about these equations. But good luck tackling your spherical coordinates problems.